Chapter 15.4, we're diving into polar integration. So grab your jackets because we're talking about polar. You may have recognized this before. It is a topic that's covered in Calculus 1 and 2, or if you took like Calculus BC in high school, you do learn a little bit about the polar coordinate system. And so that's what all it is. So polar is just a new type of coordinate system. And the only reason why we introduce it is not to make your life more difficult, but in fact, it's going to make a lot of the integrals and regions we encounter in the future much, much easier to solve, especially if they're circular or round in nature. It's going to really simplify the math that we have to do. So I want to start by doing a comparison between the rectangular coordinate system that we're used to and a polar coordinate system. So we're used to really working with rectangular coordinates, or they're also called Cartesian coordinates. So rectangular, that is where we express points as x and y, and that's a combination of two lengths. So an x length, a length in the x direction, and a length in the y direction. And by combining those two, we can express any point on the xy plane. So it spans all of R2. Okay. Similarly, we have the polar coordinate system. And that's the variables that we use for that are not x and y, but rather r and theta. R, what that variable is that is a radius from the origin. And theta is an angle. So instead of a length and a length, we now can express every point as the combination of a length and an angle. So it's an angle measured from the positive x-axis. And just like rectangular coordinates, this will also span all of R2. So the entire xy plane can be expressed with polar coordinates. Something to keep in mind, and the reason why we're introducing this is because polar is good for expressing circular regions. So good for expressing circular stuff, which means, it makes them easy. So that's why we're learning it. So let's look at the polar plane here for a second. So we're used to seeing the xy plane or the Cartesian plane with a grid on it, with lines going in the x and y directions, creating square grids. In the polar plane, instead, it's circles that are radially centered around the origin. In fact, in the polar plane, we don't call this the origin, but we rather call it the pole. Right? And this kind of looks like a top-down view of the Earth. If you're looking directly onto the North Pole, you kind of see everything radially extending out from that, circling around the world. So any point on the xy plane can be represented, like I said, with that combination of a radius and an angle. So this point right here, 2 comma pi force, right? Remember that is the radius and the angle theta. So in this case, r is here, so that's a length of 2. Right, we can verify that. And then this angle here, that is theta equals pi force. So that's our theta. Now, this point could also have been expressed in rectangular coordinates, right, where this and this would exist. So let me get rid of this. It's kind of in the way. Where this would be the y height, and that's the x length. Right, so here's our angle theta. So that x and y are the equivalent rectangular coordinate. Right, so that would exist here. And so we need a translation equation, or a way to get from rectangular to polar coordinates. So that's what we're going to get here. So the translation equations get you from rectangular to polar coordinates. to polar, and vice versa. You can apply them in reverse just as equally. All right, so that would go from rectangular to polar. So we have one for x and one for y, and x in rectangular becomes r cosine of theta, and y will become r sine theta. And these are just your triangle equations for solving for the length of sides of a right triangle. And then the third one we have is, you'll recognize x squared plus y squared is equal to r squared, right? And this set of translation equations will help us rewrite rectangular bounds and integrals into polar coordinates. So let's do an example over here. So an example, let me do one, I'll use mint for rectangular. So we have an integral of a function in rectangular coordinates, that would be like dx dy, over some region R. That becomes, in polar, still a double integral over a region. Now our function is not in terms of x and y, it's in terms of r and thetas. And now we have dr, d theta. So that's what that differential in the end becomes. But something that is a little tricky and a lot of students forget is that when you convert into polar integration, you have to remember that you actually multiply by an extra r. So an extra r gets multiplied in there, and we'll explore where that comes from in a couple sections in chapter 15.8. It's actually an area differentiable, or an area accounting factor. When you wrap the coordinate system around in a circle like this, you have a little bit of area change, and so you account for that with an extra r. But for now, just remember to multiply by that extra r in every integral you convert into polar. So we'll talk about that here. So that area differentiable in polar, that dA in rectangular, or like dx dy, that becomes r times dr d theta. So don't forget that extra r. Well, now let's talk about when to use. So when to use. So when to use polar? We use polar when the region we're integrating over, right? So this is the part on the xy plane. When that part is circular, or like circular in nature. So parts of a circle or pieces of it. So really, this is the part that tells us to use polar, and then we have to change the function we're integrating into polar coordinates just as a consequence of using the polar coordinate system. But really, we do it because the region of integration is circular, not anything to do with the function we're integrating. So the part that lives in 3D has nothing to do with it. It's just that region on the XY plane. So we'll keep that in mind as we're going through these problems. So let's start with number one. So number one, it's just asking us to bound the following regions in polar coordinates. So all I'm going to do is bound it with the two variables we have. We have an r bound and a theta bound. Right, and these are the bounds that would go on those two integrals in polar coordinates. And r, in this case, across the entire domain of the region, starts at the pole, at the origin, and goes to a length of, looks like 9. So it's from 0 to 9. And that's true across the entire domain, right? So it's always from 0 to 9. And then for theta, theta starts here. That's theta equals 0. We're not in the region initially, right? Not in the region until we hit theta equals pi halves. Then we're in the region all the way until 2 pi. So in this case, it would be from pi halves to 2 pi. And so the way we would set up an integral that would capture that region is something that looks like this. So the double integral of a function in terms of r and theta. Remember r dr d theta. And that would go from 0 to 9, and then from pi halves to 2 pi. That would give us this region of integration. So this is our r, where our function, this function here, would live above the region. So it would be in 3D, kind of above your screen. Now let's look at this one. So we'll do r is between two things, and theta is between two things. So in this case, r does not start at the origin, right? Immediately at the origin, you are not in the region. You're actually not in the region until here, right? That's true all the way around. So it's actually from 0 to 4. And that's true here and everywhere. So it's from 1 to 4. So you enter at a radius of 1 and you exit at a radius of 4. Now let's do theta. So theta for this one is a little tricky. There are two notes I want to make. So notes on theta. The first one is that theta must always be, and similarly with r, it must always be in increasing order. So you have to go from small to big. And then secondly, theta does not have to always be positive. So it does not have to be a positive number. So there are two ways to write the theta bounds for here. One way is to say theta goes from, so right here is that theta equals 0. You could go all the way around to here, or you could go all the way around and start at theta equals 3 pi halves, continue on to 2 pi, and then keep increasing. So you're going past 2 pi all the way to 5 pi halves. Right, so one way to write it is from 3 pi halves to 5 pi halves. Right, you cannot say from 3 pi halves to 2 pi halves, right? We're used to calling this 2 pi halves. If you did it that way, you'd actually be tracing out the opposite direction, right? From 3 pi halves to 2 pi halves. But we have to go in increasing order, right? That's why we need to do 3 pi halves to 5 pi halves. Now, the other way to do it, and the way I would prefer to write it, is taking into account this number 2 note, which is that theta doesn't have to be positive. So what you could do, you could equivalently write this region by starting at theta equals 0 and actually backing up pi halves and starting at negative pi halves and going to 0 and then continuing on to positive pi halves. So that's another way you could write this region. So you could write it from negative pi halves to pi halves. So you could do that or that, right? Both of them are equally valid. I prefer this one. I think it's a little bit more elegant, but either one is true. What you could not do, though, is what I said. You could not do 3 pi halves to 2 pi halves, or 3 pi halves to pi halves, right? That one is not valid. Okay, cool. So that's number 1 and number 2, and you can try setting up the integral on your own for that region. Now let's look at number 3 and number 4. So I can already tell this one's going to be tricky. How can I tell that? Because polar is really good for expressing regions that are circular in nature. So it makes circular regions really simple in polar coordinates. What it does not do, it does not express rectangular regions very well in polar coordinates. So because this region is triangular and it's already very angular, that's a good candidate for rectangular coordinates, but it's also really good practice for working with our polar coordinate system. So trying to write something that's rectangular in polar coordinates is good practice. So let's try writing this. So we're going to bound r between two things and theta. So I'm going to start with theta because we know that this is a 45-degree angle line right here. That's that point 1, 1, and this is the point negative 1, 1. All this is that's our 45-degree angle line, y equals x. So that is going to be exactly an angle of pi fourths, right? And similarly, this one over here will be 3 pi fourths. So our theta for our region will go between those two. So this is our change in theta. So that'll go from pi fourths to 3 pi fourths. Now here's the tricky one. R is going to be a little bit harder, and here's why. Because if you look at theta equals pi halves, going straight up, here's our r. It starts at 0 and it goes to 1. So here r equals 1. Now it might be tempting to say that's true across the whole region because it's a straight line. But actually, if you look at r equals pi fourths, r is a little bit longer than 1. R is actually, in this case, it would be, let's see, it would be the square root of 2, I believe. Right? And same over here. This r is also equal to the square root of 2. Right? So our r changes across the domain of the region. We start at a length of square root of 2. It gets a little bit shorter as it moves this way, and then it gets a little bit longer again as it continues on. So we need to find some equation that tells us how r changes as our theta sweeps across the region. So let me write that out for you. So if r is variable, which in this case it is, right? The radius is not the same. Then we need to write an equation for it. So we need an equation for r in terms of theta. Right, so how r is changing across the domain of the region as theta increases. So the best strategy for doing this is, first of all, identifying the equation for that line in rectangular coordinates. So this top line where r ends, in rectangular, that's a really easy equation. That's just y equals 1, or horizontal line at a height of 1. Now if we come up to our translation equations, right here, we actually have one for y. Y equals r sine theta. So if we apply that translation equation, right, so we're writing it y equals 1 is that terminal for r. That becomes r sine theta equals 1. And we need to write an equation for r. So r equals something in terms of theta. So let's solve this for r. So in this case, it would become r equals 1 over sine theta, which we know is the same thing as cosecant of theta. So that is our bound for r. It's a variable bound, but it is the bound nonetheless. So here we go. So r will go from 0 to cosecant of theta. And so that means that you can plug in this theta into here, and it'll tell you that r equals the square root of 2. Same thing here. You can plug in theta equals pi halves, and that'll give you r equals 1. Same thing over here. It'll also give you square root of 2 for that side. So it tells you how r is changing. And you can write that as an integral, right, very easily. So we would do our double integral of some function, r dr d theta, where r goes from 0 to the equation cosecant of theta. And then this goes from, what was it, pi halves, or pi fourths to 3 pi fourths. So that's how we would write that equation. Let me make this pen a little bit smaller so you can get more definition. Okay, this one is very similar as well. It's another triangular region. I'm going to let you do this one on your own because it uses the exact same techniques that we used in the last one. So that'll be good practice. Excuse me. Okay, number 9 and number 10. So in exercises 9 through 22, we're not doing 9 through 22. We'll just do 9 and 10. Change the Cartesian integral into an equivalent polar integral. So now it gave us the syntax, the mathematical expression for a certain integral in Cartesian coordinates, and we're asked to convert that into polar. So let's do it. First of all, I'm going to be looking at this region defined by these bounds, and I think a good first step is to sketch the region in rectangular coordinates, just so you know what you're working with. So first, we will sketch r in rectangular coordinates. Right. So let me get some axes. Okay. So we know for this region, r y goes from 0 to the square root of 1 minus x squared. Now this, you kind of need to know what this is. That is going to be the upper half of the unit circle. And how I got that is from our circle equation. So our circle equation in rectangular coordinates is x squared plus y squared equals 1. And if you solve that for y, you get y equals plus or minus the square root of 1 minus x squared. And so the positive portion of this gives you the upper half, and the negative portion gives you the lower half. So the combination of them trace out the entire unit circle, but in this case, we're just looking at the top half, right, from 0 to the positive square root of 1 minus x squared. So we have this, and then our x bounds go from -1 to +1. All right, so this right here is our region that we're integrating over, and we need to convert that to polar coordinates. Now this one's going to be really easy in polar. Let's do an integral. And then we have, was there a function inside? Yep, no function. So we're just integrating 1. So we'll get r dr d theta. Now our bounds for r, that's pretty easy. That's just from 0 to 1. And then for theta will be from 0 to pi. That gives us just that upper half. Right, and so this is going to be a lot easier to evaluate than that with the square root of 1 and minus x squared. This one will be much, much nicer. Okay, number 10. Same thing, I'm going to start by sketching the region in rectangular coordinates. So we'll start here. So here's x and y. Okay, so similarly, this equation 1 minus y squared, that's going to be the right half of your unit circle. And we got that from solving it not for y, but we get that from solving x. And so the x values will give you x is equal to plus or minus the square root of 1 minus y squared, and that gives you the left and right half. So because we're just asked for the positive portion, we're just getting the positive half of this, so that's this part. And then it looks like y goes between 0 and 1. So y will go from 0 to 1. So in this case, it gives us just this part. That's r. So this is going to also be pretty easy to write as well. So this will be the double integral. Let's convert this function to polar as well. X squared plus y squared. Look at our translation equations. Oh, r squared. Where'd it go? R squared times r dr d theta. These are also going to be really easy to set up in polar. That is just from 0 to 1, and then theta will be from 0 to pi halves, just to give you that quarter of a circle. And what we can do as well to clean this up a little bit is to multiply that extra r in and just do r cubed dr d theta. There we go. Number 34. So this is our first word problem, or kind of sentence structured problem of the worksheet. Let me get out a highlighter to highlight the important parts. So we're asked to find the average height of a cone. So I'm already thinking of my average value formula that we talked about in the last section. We'll pull that back out. So we're finding the average height of this cone, z equals the square root of x squared plus y squared. That is going to be our surface, right? Because z is the same as saying f of xy equals that. Above the disk, so the disk above it, this is going to be our r, our region. X squared plus y squared is less than or equal to a squared. So all this is saying is the less than or equal to is saying that normally if we were to have x squared plus y squared equals something squared, then that's just going to be the boundary of a circle. But since we're saying then that it's less than or equal to, we're actually considering the whole thing. So just filled in. It's a disk, not a circle. And this part might be a little confusing. This a squared, that's not a number, it's just a variable. All this is saying is that we're trying to find the average height of a cone over any given size circle, right? So it could be a circle of radius 1 or 2 or 1,000,000. A could be any value. And so our answer will have the variable a in it. It'll be a variable equation. So you can plug in any size circle of radius a, and it will tell you what the average height of that cone over that size circle is. So let's get rid of some of this. Okay, so this is R. Above the xy plane. So I'm going to draw a little picture of what's going on here. And we have that surface F. So I'm going to get my 3D coordinate system going. And so you should recognize that square root of x squared plus y squared is your cone centered at the origin facing up. So that's going to look something like this. So cone, let me make it a little bit fatter. It's exactly half. So here we go. Here's a cone centered at the origin. There we go. So here's F. And then what is our disk? So our disk is of radius A. So our disk could be this big. It could be like 1. It could be this. So depending on what A is, it's variable. It could be any size. So this, that's a length of A. But this whole region down here, this is R. So R is that region on the xy plane over which we're trying to find the average height of the cone. And so we would expect that as A gets bigger, right, as A gets bigger, we would expect the average value to also get bigger because we're capturing taller and taller parts of the cone. So we'll verify that with the answer, that as A gets bigger, the average height should also get bigger. I'll leave that here. So here's our R down there. So remember our average value formula is 1 over the area of R times the double integral over R of your function dA. All right, so that's the general formula. So let's apply it to this case. So now we're looking for the average height. That's going to be 1 over, and what is the area of R? Well, R is not constant, right? R could be any radius A, but it is going to be a circle. And so we know what the area of a circle of radius A is going to be. That's just going to be pi R squared, which in this case is pi A squared. So there we go. So that's 1 over the area of any circle of radius A times the double integral of our function. And what is our function? The square root of x squared plus y squared. So x squared plus y squared in polar becomes r squared, and then we take the square root of that, which just becomes r. So here we have just r dr d theta, and then our bounds for the region, r will go from 0 to a, and then, from 0 to a and r, and then theta will go from 0 to 2 pi to get the entire region. Again, we can combine these two r's into 1. This will just become r squared. So you evaluate this integral, divide it by pi a squared. I won't do all the evaluation. I'm sure you can do that on your own, but just to validate your work, the answer you're looking for is 2a over 3. So what this is saying is that for any region of radius a, so for any given region, the average height of the cone above it is exactly equal to 2 times the radius divided by 3. So we have a nice formula for finding what the average height of any cone over any size region is. Okay, the last one, last problem. This one is asking us to find the volume, and we know double integrals give you volume, between z equals 9 minus x squared minus y squared. So that's a function, right? Function of two variables. So that's like f. And the xy plane on the bottom. And the sides. So the sides are bounded by the cylinder. So that's going to give us the side bounds of the shape we're trying to find, are given by x squared plus y squared equals 1. So that is going to occur on the sides of the shape. So let's draw a picture of what's going on. Okay. So our surface here, let me do it in this color. So this is another parent function you need to know. 9 minus x squared minus y squared is, that is your paraboloid opening downwards at a height of 9. All right, so starting at a height of 9, it's going to be a paraboloid that opens down like this. Right, it'll intersect the xy plane and make a circle. So that's your surface F. And then we said bounded on the sides by the cylinder x squared plus y squared equals 1. So that's just a cylinder of radius 1 centered at the origin. So let's draw it here. What goes good with mint? Let's do salmon. So that's going to be a circle of radius 1, or excuse me, a cylinder here, extending upwards from the xy plane. So it'll probably intersect somewhere like that. And then maybe it probably is going to have some like curved top. Like that. Right, so this is the shape that we're trying to find the volume of. Looks like this. Right, where the region we're integrating over, R, is this guy. This is R, right down there. So let's set up a double integral to find that. So we're going to do the double integral of this function dA over R. So that will give us the volume of that shape. So let's plug in the pieces. So volume, and I'm going to convert to polar. Polar because R, the region, is circular. It is a circle. So this is a really good candidate for polar. So we're going to do the double integral. As a consequence, we have to convert our surface into polar. And it might be easier if I rewrite it like this. X squared plus y squared. So 9 minus the quantity x squared plus y squared, because that translates really easily into what you should recognize as 9 minus r squared times r dr d theta. And then the bounds for r, that's going to be really easy as well. So r will just go from 0 to 1. And then to get the entire circle, we'll do 0 to 2 pi. Right, that'll give us the entire domain of the region. We can multiply that extra r out. So what I'll do is I'll just replace this in here with 9r minus r cubed. And then if you evaluate that integral, you will get the volume of this kind of little cylinder with a rounded top looking shape. I'll let you evaluate it on your own, but the answer you're looking for is 17 pi halves. So if you get that, you know you did the evaluation correct.